Okay, so the first talk after our nice lunch will be by Saskia Demulder, and she's going to talk about breaking the integrability.
Indeed.
Okay.
Thank you. First of all, thanks to the organizers for organizing this very nice event and for this opportunity to present this work. So most of the work I will present will be is some work with Ratindra Das, where we studied integrability breaking for semi-classical string solutions. So if I have to situate myself in the keywords of the conference, I'm definitely kind of in deformations, but I will liberally interpret the integrability because I will only break integrability. So there will be actually no integrability here. But since on Monday, we had several times the appearance of higher loop correction to the dilatation operator, I decided to change a bit my presentation and to not only break integrability classically, but also at the quantum level. And it is more recent work with Pavel, Brian, Ratindra again, and Tristan. Okay, let's go. So really the central question that I want to understand and I want to ask is that, well, when integrability breaks, so first in terms of the semi-classical strings, but then in the gauge theory, what is actually changing with the solutions we had when we had integrability? And in particular, for the semi-classical case, how does it manifest through observables? So considering the audience, I think I will have to spend some slides kind of motivating why non-integrability is interesting. Once I've done that, I will have to do some inspirational detour in quantum chaos, because what I want to do is to take one very successful tool in quantum chaos and change it so that it works for semi-classical strings. And this new tool, I touched the button that I shouldn't touch. Oops, okay, here we go. We call Krylov, which you will understand soon. And once I have introduced this new setting, I will speak about only one example. So we did other examples, which is the higher loop correction to the SU2 dilatation operator and the associated semi-classical solution on the string side. But this example will enable me to also kind of explain our results with Tristan, Pavel, Brian, and Pavel on the quantum side of things. Okay, so let's go. Okay, so for this audience, I don't really need to motivate how important integrability is and how important it was in the holography program and still is. However, we need to face the fact that integrability is non-generic and very rare. In fact, if I take ADS5 times S5, any very legit thing that I can do to that is going to break the integrability. For example, perturbative corrections, which are this higher loop, but also 1/n corrections. If I change the internal space to something else, which is a Saskia, for example, generically, I will also not have integrability. And even if I just generically deform the S5, again, I'm losing integrability. So you're immediately confronted, once you kind of leave this regime, this integrability breaking, and some signs of chaos. Okay. So you maybe lose integrability, but by losing the integrability, you enter a regime that has a lot of physical phenomena. And it is actually well documented in the literature. So for example, you can study semi-classical solutions where you have trapping without having the need of a singularity or an horizon. You can also study solutions that have effective confinement. And okay, you can unravel a lot of kind of the chaotic dynamics on both sides of the holographic property. So these really represent a lot of features that are not accessible in the integrable regime and which represent kind of phenomena that live in a huge phase space of classical string dynamics. So then you'll say, well, very fine, but probably most of you know some measures of chaos. So why would I need another measure of chaos, right? Like we have Lyapunov exponent, we have Kovacic's algorithm, we have Poincaré sections. And these, you apply them, and you basically get an answer. Do I have chaos? Yes or no? And okay, in some sense also it's strength for example, Lyapunov exponent. But let me first point out that none of these diagnostics are logically connected. So you can have that Kovacic's theorem is telling you, oh, you're missing integrable charge, conserved charges, so your system cannot be possibly integrable. But for the life of you, you can scan as much the parameter space as you want, you will not find Lyapunov exponents, and you will not find non-trivial Poincaré sections. And it is true for any of these things. So what he's pointing out is that chaos is not something which is just one single entity. I mean, you can kind of be integrable in just one way, can be chaotic in many different ways. And how you're chaotic and how much you're chaotic in every single diagnostic is information about your system. So here I have a small illustration of, for example, when you break integrability in a classical finite dimensional system, you have that your phase space is foliated in tori. When you're going to start breaking integrability, you're going to have certain of these tori and certain pockets, for example, for certain energies, etc., that are going to gradually destroy it. And understanding how this happens and where it happens is informative. And actually, it is a collection of a lot of phenomena that are known in the literature. So I will not name all of them. I will not have the time, but we kind of looked at most of them in the paper with Ratindra. The one that I want to draw your attention to is that of filamentation, which is kind of intuitively very easy to understand, is that if you're in a phase space and I break integrability, then I will have some point in my phase space where I will have kind of very sensitive dependence on initial energy. So if I put a blob, some density there, and I initiate chaos, then because of the divergences, I will get a phenomenon which shows filamentation. My blob is no longer going to get uniform. Because I introduce some integrability breaking, potentially chaos, I will get kind of this deformation of the blob. So keep that in mind because it is going to come back. Good. So these are all different mechanisms that you can't really see with the Poincaré section, especially in higher dimensional phase spaces or with the Lyapunov exponents. So can we find a tool that enables us to unravel some of these mechanisms? And to do that, I need to make a slight detour. And the detour is going to be that in quantum chaos. So I emphasize, I am interested now in classical chaos, but quantum chaos is a much more hotter topic, especially nowadays. So we know, and we have a lot of tools in quantum chaos. And one tool that has been very popular recently is Krylov complexity, mostly because it's, well, you will understand why a bit later, but for the moment, it's very easily computational compared to computing other measures of chaos. And it's designed to kind of probe quantum chaos and especially very strongly chaotic system. So how does it work? Well, so you want to understand your system, and what you're going to do is that you're going to take a generic operator in that quantum system. Generic is very important, and I'm going to return to that. Then how complex is it going to be under time evolution? So I time evolve that, and then one thing that is, as you will see, smart to do is to apply what is called the Lanczos algorithm, and then it's going to get tridiagonal in a so-called Krylov basis. So in that Krylov basis, it takes a tridiagonal form. Why? Well, if you expand your time-evolving operator in this Krylov basis, then the Heisenberg equation is going to boil down to a very simple equation of a semi-infinite spin chain, where the parameters here are the parameters from the tridiagonalization. Why is that nice? Well, essentially what I'm doing is that now I'm able to track, by counting the number of basis elements I have, how much basis vector I need to capture the evolution of that operator. Now, if that operator is simple and it's evolving in an integrable system, then I expect that I don't need a lot of vectors, even if I wait a long time. But in a system which is chaotic, and I take a generic operator, I expect that, well, very fast, I will need exponentially many of these basis vectors to be able to describe it. It will explore the Hilbert space very, very fast. But here is where generic is important. Because even in quantum chaotic systems, you have some conserved charges. And if you happen to take an operator that overlaps with some conserved charges, then that state will not be representative of the dynamics of your system. So this is the thing that you need to be careful with, and that was also pointed out by Charlotte, but she used it to a different effect, and we'll return to that in a bit, is that you're actually looking at your system by a choice of operator, and a choice of operator is very important. But let's move on. Okay, so you have now that you're tracking the evolution of your operator according to the spin chain. And essentially, its position is going to be tracked by this wave function, which or the expansion coefficient. And what you expect is that when you have quantum chaos, that wave function is going to propagate ballistically through that spin chain. And that's where then the idea of Krylov complexity comes from, because Krylov complexity is just the average position of that wave function on this chain. So it tells you on average, at this time t, how many Krylov basis vector do I need to describe it? If it grows exponentially, well, you probably have chaos. So it's as simple as that. Now, let me show something which is slightly different. So, so I'm showing you a slightly different situation where I have again a wave function, and it has approximately the same Krylov complexity, but you can see already that its propagation is much more dispersed. It's much less ballistic. So what I want to show here is that, well, Krylov complexity is only one scalar that summarizes the evolution in the Hilbert space. You can also kind of want, for example, to ask, oh, is it evolving ergodically in a coherent way, etc. So it's kind of only the first moment of this method. Good. Okay, so this was all quantum. This is very nice. I want to have it in a classical setting. And so now I'm going to present how Ratindra and I found a way to take these ideas and apply them in a classical setting. And I want to point out that a few days ago, there was a paper by Dero, Sanchez, Garrido, and Zonner that was also defining a notion of classical Krylov complexity, which is very different than this one. This one is much more amenable to weak, well, integrability breaking and weak chaos, especially what you need for these string solutions. Okay. Bon, I will move closer. And that was too close. Okay. So one thing that I want to point out is that I'm interested in breaking integrability in classical string solutions. So first of all, you expect to have chaos which is weak. So I don't expect to have a ballistic propagation for it. I actually expect a scenario which was closer to the other, kind of a dispersed propagation. Then, and that's what I was emphasizing a lot, is that in this quantum chaotic system, you usually look at systems which are maximally chaotic. So you have to be very unlucky to pick one operator which is not representative of the system. Here is the opposite. Which of my states I'm going to choose is going to provide me information on what is actually the chaos. Which of my observable in this case will see the chaos and which not. Okay, good. And that's the most important point, is that classically the chaos comes from non-linearities. Okay, and the way how to kind of unlock these ideas to the classical realm is to something which is called Koopman-von Neumann theory. So what is that? Okay, so you all know that when you have a system which is very nonlinear, it has more chances to be chaotic. A linear system will never be chaotic. So classically, you usually have a differential equation which is highly nonlinear. But okay, nonlinear differential equations, they're very pretty, but usually we can't do much with them. We can only look at them. So kind of motivated by that, in the 1930s, Koopman and a bit later von Neumann kind of reformulated that. It is, okay, fine, we don't want this nonlinearity. And to do that, instead of kind of looking at your system on phase space as a phase space evolution, they realized that if instead they look at the Hilbert space of observables, which are just the functions of phase space, the problem becomes a linear operator, this UF, but of course, this nonlinearity, you cannot completely get rid of them. And the expense comes through the fact that this linear operator is an infinite dimension operator. In particular, it's a differential operator. But that's very good because now we at least have a setting where we have a linear operator. It's not finite dimensional, so we cannot diagonalize it for now, but that's not a problem. Because Koopman theory is actually big business. You have many, many people working with that, understandably, because nonlinear differential equations, you do want to solve them, and this is one way to do that. And they have many, many fancy methods to how to deal with this infinite operator and put it on a computer. The method that we chose is this GEDMD, and it's rather technical, but you only need to know the ID, because the ID is very simple. So if I give you a function which is extremely complicated, I do not give you the functional form. The only thing I tell you is that, well, you have to work with this. Well, as long as I allow you to work with a polynomial of highly enough degree, which you can fit the function, you'll be just fine. This GEDMD uses exactly the same method. You're going to take a basis of monomials, and trigonometric function of a certain frequency, and you're going to apply your differential operator. You're then going to get to project that under this matrix, this basis, and you get a finite dimensional representation of the dimensions of a basis. And if you take rich enough number of polynomials and trigonometric functions, you will have a very good approximation of this infinite dimensional dynamics. Here we go. So this is essentially this GADMT. So at the end of the day, then, what you get, no, it's too fast, is that we get an approximation of this linear operator that is exactly capturing this nonlinear problem. And okay, so that means that now you have a matrix, you can tridiagonalize it, and you can study the propagation or the evolution of your operator in the Hilbert space as a spin chain in exactly the same way. And okay, we call this thing then also Krylov to highlight the importance of this Krylov formalism. Okay, good. So now we have this Krylov formalism. And as I was pointing out, this Krylov business is much more than Krylov complexity, because it has many, many moments that you can compute from this wave function that explains the spread, which is the complexity, but also the delocalization, how the wave function is spreading. You can also look at spectral transport and filamentation of peak at the end. But again, I really want to emphasize here, it's very different from Krylov complexity, is that here, which observables are going to see which one of the signatures is going to tell you about the system. Is it the momentum? Is it the energy? Is it some type of angular momentum, etc.? And okay, so far as we could see, the signatures are not universal. Maybe there is some universality, but we looked at a very different example, more to test our method. So we couldn't find any universality so far. And okay, so now let's look at some examples. But before showing the exact examples, I need to introduce a little bit what this system is. So I'm going to look at higher loop correction to the dilatation operator. So this already came several times during the conference, so I'll be a little bit quick, is that we look at the anomalous correction to the scaling dimension of single trace operators. And this anomalous dimension at one loop is integrable because it was realized that this, I only do SU2 for simplicity, is the Heisenberg spin chain. So it is integrable and at one loop. And you can see this dilatation operator just as a spin chain. Now, you have, of course, higher loop corrections. And in terms of the spin chain, it's quite nice because the higher loop correction, if I, for example, introduce the second loop, at the level of the spin chain is very intuitive because what you're going to do is that instead of having just next neighbor interaction, you get next to next neighbor interaction. And every time you add a higher loop, you're going to go one further in the interaction. Now, this is quantum. I first want to do classical. So as was observed by Kruszewski and Zeitlin, is that when you take a semi-classical limit of this dilatation operator with this Landau-Lifshitz limit, you will see that the action you get is equivalent to the action of a propagating strings in a subsector that correspond to the subsector you chose for the dilatation operator, such that you can get from this dilatation operator some equations. And if you take the higher loop corrections, you will get deformed motion through this higher loop contribution to the integrable solution. And these are the deformations we are going to consider. And I want to ask on both sides, how does integrability and chaos manifest on each side? Okay, so I first start in the classical regime. So for the classical regime, I was going to use my Krylov. So I can write down the nonlinear differential system that's essentially this vector characterized the nonlinear differential equation. And it, as was studied some years ago by McLaughlin and Spearing, that system is weakly integrable. You have to work hard to find a Lyapunov exponents. But we can be much more precise with this Krylov formalism. And we can write down the Koopman operator, which is a differential operator. We throw it through the GEDMD method, and we get a finite dimensional matrix. Okay, and so what we do is that we look at the integrable system, we look at the chaotic system, or the integrability breaking system, and we're going to compare the signatures in terms of chaos and see how the propagation in Hilbert space. So here I just took, so we looked at many other things, but here, for example, I look at some type of energy and some type of momentum in integrable case and in a chaotic case. Notice, and it will be important, is that when you're introducing the deformation, you're enhancing the phase space. So in the integral case, I have a two-dimensional phase space. In my default model, the deformation introduces a phase space which is four-dimensional. Okay, so the colors are working. Okay, so the dashed line is always the integrable system, and the full line is always kind of the integrability breaking system. And here I've plotted the Krylov complexity. It's kind of the first thing that you do with Krylov complexity. And you see that here it's very clear that indeed in integrability breaking, you will have that these operators are going to go propagate much faster and becomes much more complex much faster than just the integrable case. No, but you can also ask, okay, they go much faster, but what about the delocalization? So here we have two measures. One is called the IPR and the other the entropy. Their details are not so important in that they both measure how the wave function is going to delocalize in the semi-infinite spin chain, or how coherent they're going to, or ballistically or not, they are going to go through the spin chain. And what we see is that not only are they going to go ballistically, they don't go as ballistically as in the quantum case, for sure not, but they're also going to spread much more than the integrable case in both cases. So one is a measure of the concentration of the dominant Krylov weight, and the other one is the entropy that kind of measures the disorder in that Krylov distribution. And this is kind of the picture. One is much more coherent and the other one not. Good, so filamentation is something, for example, that you cannot see with the Lyapunov exponents, and well, not really either with kind of Poincaré sections. So I was explaining this with this cartoon, but kind of in this cartoon, I can make a bit more concrete in this example. Because as I was telling you, in the integrable case, I have a two-dimensional phase space. Once I introduce the deformation, I'm actually enhancing my phase space to extra dimensions. So here, I can actually, with my Krylov method, kind of capture the modes that are escaping from the integrable phase space. Because now I have a Hilbert space, and I can just divide my Hilbert space in functions that just depend on this and the rest. And then I can see which observables are actually sensitive and are going to give this filamentation phenomena. There are much more details in the paper for which observables we're doing that, but we can do this with this Krylov complexity, this scope and Krylov probes. Very good. Okay, so this was classical. So now, since this quantum case was mentioned several times on Monday, I did want to include some slides that were kind of covering the analogous, well, the same system, but on the quantum side. So now I'm dealing with higher loop correction to the spin chains, which you can see as increasing higher order interactions or longer range interactions. How does the chaos manifest here? So one thing that you need to know is that, well, the first loop, as I already said, it's integrable. Every single loop you're going to introduce is going to break integrability. But okay, there is overwhelming evidence that once you add all the loops, so you have the all loop dilatation operator, your system is again integrable. Okay, so but we don't have access to the all loop. The only thing we have access to, for which we have expression, is the first loop, the second loop, the three loop, and the four loop. And this is what we studied with Tristan, Brian, Pavel, and Ratinder. And you just get every time, the colors are better there, like higher order interactions. Good, and the image, if you just want to have an image of the result that we got, is this one. So what do we see here is that here you're integrable, and when you go up, you get more and more signatures of chaos, and you're full on chaos at the top of this graph. Now, you start with something which is integrable, you end with something which is integrable. What happens in between? And what we show that in between is that you are never going to be strongly chaotic. Actually, all these systems are weakly chaotic, and you would maybe expect that it kind of goes down, like in a monotonic way, to being integrable, and that's not the case. There is kind of an odd, even odd effect. And okay, so how did we show this? Because we computed kind of conventional spectral chaos measures and also Krylov, normal Krylov complexity for this spin chain. Okay, let me go more in detail. So the most standard way of looking at Krylov in many body systems and in spin chain is through eigenvalue chaos. So you diagonalize your finite dimensional Hamiltonians and you get the energies. And you're going to look at how these energies are distributed. Now, if you have an integrable system, you have a lot of conserved charges, so you expect to have a lot of degeneracies. So many of these energies are just going to sit at the same place. In a quantum chaotic system, you have close to no conserved charges. They have no reason to have degeneracies. So what you get is what people call level repulsion. because they have no reason to sit together. So something that you can plot then is kind of the differences between subsequent energies. And there are conjectures which have a lot of evidence is that, well, if you have an integrable system, you get a Poisson, because most differences lie at zero. They are degenerate. But if you have a quantum system, you have no reason to have degeneracies, and it lies somewhere non-zero, the center of mass of the distribution. And okay, this depends on which, you have GOE, GUE, it depends on your symmetries, but here it will be GOE. Okay, so this is kind of the basics. And we computed that for all the spin chains. And I'm not showing you these distributions because there are a lot of subtleties that I want to shove under the rug. So instead, I'm going to show you something else, which is this R ratio. And this R ratio is very simple. It's just a ratio of these differences between the energy levels, but it doesn't have the same problems. And here you see a plot of this R ratio. So it has a universal value from when you have Poisson, which is here. It has a universal value when you are GOE, which is here. The red, which you're seeing, is essentially a non-integrable beta deformation of the spin chain. As you see, okay, once I turn on the deformation parameter, G, it goes straight to GOE, immediately chaotic. But for the other spin chains, so for the 2-loop, the 3-loop, and the 4-loop, I get something more interesting. First of all, it takes a bit more, I have to crank up the deformation parameter quite a bit more in order for it to really become chaotic. And 3-loop actually barely becomes chaotic. I get even an odd effect, chaotic, barely chaotic, and again chaotic. Now here you need to be careful is that I'm plotting beyond the convergence radius of the perturbative expansion for the loop. However, it's still interesting because when you go beyond that convergence radius, you just have a spin chain, and condensed matter physicists love spin chains, so there is nothing else there. But it's just no longer holographic, or not expected to be. Okay, so this eigenvalue chaos, how much am I doing with time? Hoeveel? Oh, ça va. Okay. So for those of you that are still alive after lunch, maybe you might have complained that, well, when I'm having the eigensystem of a matrix, it's not only characterized by its eigenvalues, but also the eigenvectors. So is there any information about the chaos in the eigenvectors? Yes, there is one. It's a less conventional way of looking at chaos, but here it's very informative. So this eigenvector chaos, what you do is that now you look at your eigenvectors, and you're going to pick a reference basis which you consider to be very ordered. What is here very ordered? Well, it's kind of the spin product basis of my up and down spins on that spin chain. And then you're going to expand the eigenvectors in that reference basis. You can take another choice. So we made other choices, but this is one standard choice that people do in the literature. And then you're going to see how dispersed is that eigenvector system in this ordered basis. And when it's very disordered, well, when it's not very, well, when it's kind of delocalized, you actually have a system that has a lot of disorder, is ergodic. While if it's very organized, then usually you have an integrable system. Okay, so again, a plot to exemplify that in the system. So on the top, you have this line is if you had a perfect GOE. So you have a matrix model, which is GOE, then what would happen is that every single dot here is an eigenvector, is a state according to its energy. If it were purely GOE, they all had to sit kind of that line. This is absolutely not what is happening. So as you can see, most of them are much lower in this kind of this fractal dimension that quantifies the disorder. And that means that in a spin chain, you only have very few states which are ergodic. Although they do hit the GOE in terms of the eigenvalues, in terms of the eigenvectors, they are barely ergodic. So in this additional sense, it's very weakly chaotic. Good. Okay, so I told you about eigenvector chaos, about eigenvalue chaos, and we also wanted to look at Krylov complexity because Krylov complexity does something that the two others cannot. So let me just quickly review. So now you need to be careful because there are two types of quantum Krylov complexity, one for operators and one for states. Heisenberg picture, Schrödinger picture. The difference is a minus sign, and minus signs matters in life, so it's a bit different. But okay. But the procedure is exactly the same. I take my states, I build my Krylov basis, and I'm going to study the propagation of the associated wave function through the auxiliary spin chain, and I'm looking how fast it goes, how spread it goes, etc. But the important thing here to notice is that Krylov complex is very different from these kind of spectral measures of chaos. Now, the spectral measure of chaos, I was looking individually at the eigenvalues and individually at the eigenvectors. Krylov complexity is just mixing both of them. Because yes, I'm acting, okay, I'm acting with my Hamiltonian, but I have to pick a certain eigenstate, a certain initial state, which is going to be essentially a certain choice of eigenvectors. So it mixes these two quantities in an intertwined way. Good. Okay, so in the paper, you will find these kind of plots, which definitely goes beyond the abilities of the beamer. So I'm going to simplify that in a second, but I need to first tell you about how to read these plots. So I'm going Krylov complexity. So I'm choosing an initial state, which is just this particular linear combination of the energy eigenstates. And these are plots for the two-loop deformation. So instead, I'm going to isolate two lines, one which is at kind of low deformation parameter and one which is high deformation parameter. So for this state Krylov complexity, these guys worked out that in order to have this ballistic growth, this translating this plot as, first of all, having a higher value of the complexity, but also having a peak. And that peak corresponds to the fact that you're propagating ballistically, very coherently, so you kind of overshoot the average value of its position in the spin chain. So in some sense, both the value of the plateau and the peak are an indication of having something which is chaotic. So here we would say that for this G, the system is integrable, chaotic, and for this one, it is not really. Well, it's not chaotic, but it's very barely. Okay, and so what I'm plotting here is a correlation graph between the R ratio that we saw earlier, right? When it was kind of low, it was Poisson. When this was kind of high, it was GOE, chaos, integrability. And we have some quantity to quantify the peak. And we see that indeed, Krylov complexity, at least for the eigenvalues, is very closely tracking. So you get direct information about the eigenvalue chaos from the from Krylov complexity. So this is something that was known, not for this system, but has been studied multiple times. Now, what about state dependence? And here, state dependence, it's much, much more subtle. So again, we have this kind of graphs, which for the sake of everyone's happiness, I'm going to simplify. So here, I'm again doing exactly the same thing. I have a line at small g and a line at high g. And for this particular choice of a state, where we choose a domain wall in a spin chain, so we have all spin ups and then suddenly all spin down, we see that its ergodicity for low g is going to be not very ergodic in that spin product basis, while when you're cranking up g, it's going to be much more ergodic. And we see that, well, in this case, it seems that Krylov complexity is tracking it. So at least that state seems to be sensitive to the chaos in the Hamiltonian. But if you look at the different states, actually something very stupid, you just can take a single energy eigenstate. And there, what you see is quite different, because this one seems to be not very sensitive to that. Or at least it's kind of equally ergodic over the same line, but you get a difference in behavior in the Krylov complexity. They kind of have the same Hilbert space kind of scope, but this one has clearly a peak, while the other is not. So here again, we see that this kind of weakly chaotic system has a sensitivity to the states. So we actually don't have an explanation to why this one sees the chaos. And well, you kind of can argument that just this one is very simple and this one is much more complicated. So this one sees the dynamics much more, but it is not a very satisfying explanation. So it's something that we have observed, but we cannot really explain. Okay, that brings me to my summary. So kind of the main philosophy was that, well, I want to understand how chaos manifests once I go away from the integrable sector in string theory. And how did I do that? Well, I defined a probe, Krylov probes, for the classical chaos and how to compute them and what to actually compute to actually get a handle of what was happening. And I show you how the signatures of chaos manifest both on the classical side and on the quantum side for these two loop, for this higher loop correction to the dilatation operator. We did many more examples for the classical case, but I will spare you those. So, oops, okay, nope, that's too fast. So once we have this, you might then want to ask, okay, how well can I track these different phenomena that you cannot see with Lyapunov exponents or with Poincare sections? And okay, here you had kind of, maybe you will say boring example, because I just have perturbative correction, which I know at the end of the day are going to be integrable again. I not really get any new physics. Well, you do have, for example, 1/n corrections, where you have then interacting string and splitting and joining, that would again give you a system which is chaotic and will give you a new physics. But kind of the message that I want to make here is that it's not because you're breaking integrability that all hell breaks loose. In fact, these systems seems to be very weakly chaotic. And actually, with the very nice talk of Milos this morning, it's not because you're breaking integrability that you need to throw integrability out of the window. When you have weak chaos or integrability breaking, you can still use this integrability as a structure to compute then things in those systems. Okay, thank you very much.
Questions?
Thank you for the nice talk. I have a question, a couple of questions, but maybe I can start with this one. So if I start with the spin chain, there are conserved charges and there are operators that act on more and more sides. So in principle, I could, this two loop operator that you have, you could see essentially how far it's from the next conserved charge. And
So,
have you tried this way of thinking?
You can do this way of thinking. Actually, Marius has worked kind of in this direction to kind of do infinitesimal deformations away from an integrable system and then to see how it translates into the conserved charges. We didn't look into that, but indeed it would be very interesting.
This might be a way of explaining, maybe with these two corrections, you're somehow
yes. Yeah, I completely agree. It is something that we thought about and then never did.
Mm-hmm. And I had another question. So another question is, I'm a bit confused with this measure of spread in the Hilbert space. You said that when it's ergodic, then it's spread over.
So you mean with the eigenvector chaos?
Yes, yes.
Yes.
In the spin basis, because if I take a kind of random eigenstate of an XXX Hamiltonian, this will be it will have in this reference basis, it will be all over the places.
Yeah, but here first of all, you take a reference basis which is ordered. So we took this spin product basis, but we also just look at the eigenbasis of the integrable system and then compare this eigenbasis with the eigenbasis of the higher loop corrections. And we compare, the only thing we compare, we use a thing to expand it over is this eigenbasis, nothing else. So we don't take a random states, we just take the eigenbasis of the one loop Hamiltonian, then the two loop correction, three loop correction, four loop correction. And actually the integrable, when we take as reference basis the integrable Hamiltonian, the signatures are very similar, at least qualitatively. The values are different.
I mean, there's still something that it's against my intuition. And I have a last comment, is this about this the effect of these different initial states?
Yes.
At the very end of your talk. I mean, isn't this an effect that essentially when you choose the second state, you're essentially kind of at the edge of the Hilbert space? I mean, with energy-wise, you're not somewhere in the middle of the spectrum. And then it's things like eigenstate thermalization hypothesis would not work there, etc.
Oh, so the interpretation in terms of the eigenvalue thermalization hypothesis is something that we explored, but we couldn't reach conclusions. So I can't really say something very convincing there, actually.
My expectation would be that in the first case, you're somewhere in the middle of the Hilbert space.
But how do you order your Hilbert space? How do you?
Energy-wise, your initial state
okay, energy-wise?
Somewhere in the middle of the...
But here I can take an eigenstate of an energy of any value I want, right? Like.
Right, okay. Okay, then I don't...
No, but if you have ideas, we can speak later.
Mm-hmm.
So I somehow have the impression this Krylov complexity is very qualitative phenomenological somehow. I mean, I'm missing a little bit of quantitative content like this mean level spacing ratio that you can compare chaotic with integrable system. But so you said, for instance, that if the complexity grows exponential, then it's probably chaotic, as you say. So is there a precise statement of this type? Does it have to grow exponentially for how long and so on?
No,
You
no.
can measure.
So there is, sorry.
Is there some measure you can extract about how it grows at the beginning?
So indeed, like I completely agree with you, and that's also something I'm struggling with because at the end of the day, I come from integrability. These things are very often phenomenological, and they are proven in certain cases. So for example, so also the signatures in state complexity and operator complexity are different. And in operator complexity, they do have partial proofs for certain things, and for the rest, they just hope it works. They see that it's respected in certain systems, but in other systems not. So it is something which is phenomenological. You can be rigorous to a certain extent, and actually mathematically, the scale of complexity can be also very interesting because it's the same as actually studying orthogonal polynomials, and you can actually do analytics if you're lucky enough to end up with understanding which polynomials you have, which happens in certain situations.
Problem models which can be solved.
Sorry?
You have to land on some solvable problem.
Yeah, exactly. So
then you said some measure for the height of that peak.
yeah, so it's rather simple. So basically, it is just that you're going to measure the difference between kind of this average value there and the value at its highest value. It was repetitive, but I think you got the message. So this kind, and okay, sometimes it happened to be negative, and then we just set it to 0. That's why in this plot you have a lot of zeros.
Yeah,
and that's the reason.
Okay.
Thanks for the talk. So for these long range deformations, I guess the papers that you were citing, they also show that you have, it's still an infinite tower of local commuting charges, even at higher range. So how does that coincide with do you have any explanation of how that coincides with signatures of weak chaos?
I think it goes a little bit in the direction of the comment of Miloš to understand what is actually kind of the interaction between the conserved charges and the Hamiltonian we are working with. And so the same answer, I don't know.
Well, it's kind of a general question.
Okay.
Maybe you know answer, maybe not.
Okay.
Is it possible to cut the integrability tail piece by piece? What I mean, integrability tail piece by piece. What I mean, you have an integrable system. It has some number of integrals of motion. If it's a spin chain of finite length, it will be finite number of integrals of motion, let's say n. Would it be possible to deform your spin chain so that the system still have, say, n-1 integrals of motion? Only one of these integrals would disappear.
So I don't have an answer, but I have the very clear message that we should really look at the conserved charges.
Well, that's definitely the case. Okay, that's